So is the slides visible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so in the last class, the last topic was Gauss-Stodler theorem, and we studied about it. You can first of all go through the Gauss-Stodler theorem. Gauss-Stodler theorem states that the rate of loss of available energy or exergy in a process is proportional to rate of entropy generation. Okay, if equations 8.65 and 8.66 are written in the rate form, then the value of irreversibility is given by W lost, which is equal to T naught delta S universe, which is equal to T naught into delta into S generated. This is also known as Gauss-Stodler equation. So this is Gauss-Stodler equation, and this one was the theorem that the rate of loss of available energy or exergy in a process is proportional to rate of entropy generation. Okay, so I think it is clear to you. Now let us move to the next topic. It is about applications of Gauss-Stodler equation. Now let us see. First of all, it is being applied to heat transfer through a finite temperature difference. We have already discussed about this topic in entropy chapter also, that when the heat is transferred through finite temperature difference, there is entropy generation. Now we are going to relate that to loss of available energy. So let us see what is given to us in this diagram. We are given with the two thermal reservoir. One is at temperature T1, other is at temperature T2. Okay, so what is happening? We can say that the temperature T1 is greater than temperature T2, and the heat transfer Q dot is leaving the high temperature reservoir and going to the low temperature reservoir here. So heat is being transferred between two reservoirs. Now what happens when the heat is transferred? You know, from the entropy chapter also we have studied this topic. There is entropy generation. Okay, we can assume that this is the system, and suppose this high temperature thermal reservoir is in surroundings. Okay, so let us see what is the amount of the entropy generation. So we can write the entropy generation term as Q dot divided by T2. So Q dot divided by T2, because this is the heat which is entering into the system and entering from at temperature T2 minus entropy change of the surroundings. So it is y minus, it is actually plus minus of Q heat leaving the surroundings divided by temperature T1. So this is nothing but this term is actually equal to S generated is equal to delta S for the system plus delta S for the surroundings. So when we calculate the delta S for the surroundings, heat is entering into it. So we take it as a positive quantity Q by T2, and for delta S surrounding, because the heat is taking leaving the system, so we'll take it as negative. So it is Q dot divided by T1. And when we calculate, we get this particular value Q dot T1 minus T2, T1 minus T by T1 T2. And then from this particular equation, I have calculated the value of Q dot. Okay, so you can see it's simple jugglery, and we are able to calculate the value of Q, and that comes out to be as generated T1 T2 divided by T1 minus T2. Now let us calculate the value of the W lost. Now what is the value of the W lost actually? Now W lost is, see, we have a source at temperature T1 and a sink at temperature T2, and if we want to know how much work is available from it, what we can do is we can use a reversible heat engine as shown in this particular right diagram. Okay, so here we have a reversible heat engine. So we know that we are supplying Q dot heat to this reversible heat engine. It is producing W dot amount of the work, and this is the heat which is going to the low temperature reservoir. Okay, forget about this brake system which is shown after this W actually. So for the timing, you just see this. Now let us compare both of these two systems. The one in which We have two reservoirs only, and the heat is being transferred from T1 to T2, the left diagram, and the right diagram in which there is a heat engine where we are producing work which is equal to W actually. So the name of the topic is heat transfer through finite temperature difference. Now, what does it means actually when we are transferring heat? What is actually happening? It is only giving us entropy generation, nothing else. Okay, but if we are employing a heat engine, then we are able to get the work which is equivalent to W. It means we are losing certain amount of work. Okay, had we transferred the heat with the help of a reversible heat engine, we would have got work which is equal to W, which now we in this present case we are not getting it actually. Okay, so whatever was the work which was available to us, that is lost. And what is the value of this W if you calculate it? This is a reversible heat engine operating between T1 and T2. So the value of W will be equal to Q1 minus T2 divided by T1. So this all work which is produced is lost. So that is why in this equation, you can see this particular equation. What is written here? This is work lost. This is the work which is generated by the heat engine, but this is lost in the first system A, where the heat is being transferred through finite temperature difference. So now in the next line, what we are doing, we are putting the value of Q. This value is now written as taken from this particular equation. So we are putting it here, okay, because it was equal to Q. Now you see it. What do you get finally? You get this T1 minus T2 cancels out with T1 minus T2. T1 and T1 cancels out. We are getting T2 into S generated. So this is the value of W lost, because in this case the lower temperature was T2. So now the value of work lost is equal to T2 into S generated. And actually this work is that whole work which was generated actually with the help of a reversible heat engine. We are not getting any work. So that means we are losing work when the heat is transferred through a finite temperature difference. Here what has been shown is that now what exactly is being done in case of heat transfer to finite temperature difference. They are saying that in diagram B, the work W is generated, and then what we are doing, we are applying the brakes. When we are applying the brakes, all this work is lost as heat. So this is going to the low temperature reservoir, and that is the, you can say, work lost as heat actually. Okay, no other reason they have shown the brake actually. Okay, so this is the same thing. You can see if the heat is transferred Q from T1 to T2 and it takes place through reversible heat engine E, the entire work output W is dissipated in the brake, from which an equal amount of heat is rejected to the reservoir at temperature T2. Heat transfer through a finite temperature difference is equivalent to destruction of exergy. Now this exergy is high grade energy. So when we are transferring heat through a finite temperature difference, we are destructing the exergy or the maximum work. It is the destruction of the maximum work. Okay, I hope this is clear to you. Let us proceed to the next topic. It is about flow with friction. So what is being considered here? We have a pipeline here, which is basically a insulated pipeline. You can see it here. It's an insulated pipeline, and at entry the pressure is P1, at the exit the pressure is P2, and delta P is the loss of pressure, which is equal to P1 minus P2. Outside it's insulated, so that means no heat transfer is taking place from outside to inside or from inside to outside. And we want to know what is the loss of the available energy. Okay, so let us consider the steady and adiabatic flow of an ideal gas through a segment of a pipe. First line I have read. So now first they are writing the first law of thermodynamics. It says that H1 is equal to H2. How it can be H1 is equal to H2? Let us try to understand. We are considering this pipe as an open system. So what I can write is delta Q minus delta Ws is equal to dH plus dke plus dE. So we say that the level at inlet and outlet is same. So potential energy change is not there. It is zero. Because the pipeline is same, it's a gas. If there is no minor change in the pressure, the density will not change, the kinetic energy will not change. So we are neglecting it. Okay, we are neglecting it. Then, is there any shaft in it? No, there is no shaft. So shaft work goes. Then the system is insulated. The value of W delta Q is equal to 0. So we are left with only one single term, which is equal to dH. So it means H1 is equal to H2 when the gas is flowing through this pipe actually. Okay. Next, what we can do is we can apply the second law of thermodynamics, and we can write the equation TdS is equal to dH minus VdP. So the minus sign is not showing here. It's minus VdP. Okay. Now H1 is equal to H2. We already know it's 0 from the first law of thermodynamics. So this term actually goes. So we are left with TdS is equal to minus VdP. Minus VdP. Okay, so let us see what is ds equal to in the next equation. This is not there. This is 0. So forget about it. So ds integrating between 1 to 2 is equal to minus v by t integral 1 to 2 d for dp. Now we know it's a perfect gas. Okay. So when we have a perfect gas, we know the relation PV is equal to RT. PV is equal to RT. This is the relationship which is available to us. So I can calculate V by T is equal to R by P. So what I can do, I can put this equation here. So you can see. Now this entropy change is what actually? This is a adiabatic flow. Okay. It's a flow which is full of friction. There is pipe friction. So it's basically generating the entropy. So that entropy generation is equal to m dot into ds. Okay, don't worry about this. They have just multiplied by the mass flow rate actually, which is taking place. Otherwise, you can calculate it on the basis of unit mass also. Okay, so this v by t is now replaced by r by p here, and m dot is multiplied because it's showing the mass flow rate, and this term and this integration is from p1 to p2, and then you can integrate it and you will get this particular value. So this is the value of the entropy generation. Then later on what they have done is they have expanded this term. It is equal to mr with a negative sign log of 1 minus delta p by p1. So don't worry about this term. It's simple because I can always say that p1 minus p2 is equal to delta p. Okay, so when you will calculate the value of 1 minus delta p by p1, it will be actually equal to p2 by p1 only. And then I think this is the expansion of log term, which is that is why we are getting this particular value. So this has been expanded. This is given in the next slide. So finally the expression comes out to be for the entropy generation. Entropy generation value comes out to be m dot r into delta p by p. So basically this is the value of entropy generation then when the flow is taking place with friction, and it's a adiabatic flow. So let us see further. See, where log 1 minus delta p by p is approximated as minus delta p by p, since delta p by p1 is less than 1. Okay, the higher terms are neglected. So actually I would like to let you know that this term log, naturally if I take 1 minus x, the value if I expand it will be equal to minus x cube by 3 minus x 5 divided by 5 and so on. So where x is less than 1. Okay, and what we can do is when we neglect the higher terms, that means if we neglect this term and this term, we are left with only the value minus x. So log 1 by minus x is equal to minus x, where x is less than 1. So let us see the previous slides. You can see it here also. This is now x. Okay, so it is approximated as minus delta p by p1, which is less than 1. Okay, higher terms has been neglected. So uh, let us see what is the value of w lost now. W lost is b1 minus b2. What is the meaning of b1 minus b2? b2 is nothing but it is Keenan function. Okay, I hope you remember this. b1 is equal to Keenan function given by H minus E naught S. And velocities we have already considered constant, kinetic energy considered constant. So it is equal to V1 minus V2 between two state points. Okay, we just have calculated the value of entropy generation. Now we are calculating what is the value of W lost. So what does it comes out to be? It is equal to H1 minus T naught S1 minus H2 minus T naught S2, which is equal to, you see, H1 minus H2. Okay. Why it is equal to, see, H1 minus H2 has been, this term has been cancelled, because in the previous slide you can see this is the equation, H1 is equal to H2. Okay, so this has been cancelled, so we are only left with m dot T naught S2 minus S1. So this term is nothing but entropy generation. This whole term is entropy generation besides T naught. Okay, forget about T naught. M into S2 minus S1 is entropy generation, and then we put the value of entropy generation, which is actually mr into delta p by p1. So that is the work lost. Okay, so we have just multiplied this particular equation, of entropy generation with the value T naught. Okay, I hope this is clear to you. The decrease in availability or lost work is proportional to pressure drop now. Okay, you can see this W lost is directly proportional to delta P. Okay, and the mass flow rate also. Mass flow rate. Okay, it is shown on the right hand side by Grossman diagram, the width being proportional to the availability or exergy of the stream. It is an adoption of Sankey diagram used for energy transfer. So you just see these diagrams, actually they are talking about this particular diagram. What they are saying, that at the inlet the exergy which was available was equal to m dot into B. This is nothing but, you can say, B1. This much is the work which is available at inlet, and at the outlet this much is work which is left, and this much is the work lost. So for the lost work they are showing it downward. So this work has, you can say, lost totality, in totality. So this was the initial exergy and this is the final exergy, and the difference of two is the work lost. Now let us go to the next slide. It talks about mixing of two fluids. Now mixing of two fluids, as you know, results in uh, generation of entropy. This you have already studied in your entropy chapter. So here we are going to discuss that topic once again. Two streams 1 and 2 of an incompressible fluid or ideal gas mix adiabatically at constant pressure. So pressure has been considered constant now. Okay, there is no change in the pressure, and it's a incompressible fluid, means it cannot be compressed, or an ideal gas mixture. Okay, anything, it could be anything actually, but the pressure is constant. Now what is happening? We have m1 mass of one stream, m2 mass of other stream. When they are leaving, the total mass is m3. You can see this value of q, whether it is going in or going out, this value is 0. There is no heat transfer because it is insulated, system is insulated. So naturally the principle of exergy always says, or say exergy balance says, that the inlet exergy will always be more than the outlet exergy. There will be some exergy which will be lost. Basically it means the work which is available at inlet, the maximum work which is available corresponding to inlet condition, is always greater than the work which is leaving at the outlet condition. Okay, so what is, why there is reduction? The reduction is because of W lost. So we want to calculate for this particular case also, how much is the exergy destroyed, exergy lost, availability lost, work lost. Okay, that is what we want to calculate. So first of all, this is the mass balance equation. M1 plus M2 is equal to M3, which has been stated equal to M dot also, say. Now we have defined a term X. X is nothing but ratio of the mass of one stream number 1 to the total mass. Okay, so X is mass of stream number 1 divided by the total mass. So keep it in mind. So what will be the, if I say what is the value of 1 minus X So 1 minus x will be equal to nothing but 1 minus m1 divided by m actually. So it will be equal to m2 divided by m1 plus m2. Okay. So x is m1 by m1 plus m2 and 1 minus x is m2 over total mass. Okay. So by first law of thermodynamics, what we can write is we can write the energy balance m1 h1 plus m2 h2 is equal to m1 plus m2 into h3. And then we have divided the whole equation by m3. So this whole equation is divided by m3, which is nothing but m1 plus m2. Okay, whole equation. So you know that if I divide the first term by total m, it will become x h1. Similarly, second term will be 1 minus x h2, and third term will be equal to h3 because m3 is equal to m1 plus m2. The preceding equation may be written in the following form. Okay, now this equation which is given here, if I am considering a gas, okay, if I am considering a gas, then H is equal to CPT. So Cp will be cancelled out from everywhere. So we are left with xt1 1 minus xt2 is equal to T3, and then dividing the whole equation by T1. So T3 by T1 is equal to x plus 1 minus x, and tau. Tau is nothing but T2 by T1. So it's quite simple. So let us see now. Now let us write the entropy generation equation. So once again, let me show you the diagram. Let me draw the diagram. So this is the diagram actually. Okay, 1, here we have 2, here we have outside it is 3. Okay, now what is entropy generation? Entropy generation principle is also simple. See, whatever is the entropy entering, that should always be equal to entropy leaving plus entropy generation. Okay, entropy leaving plus entropy generation. So okay, so let us see. I think it's there is some mistake. Okay, let me see. Is it okay or not? Yes, tell me. See, actually, final entropy will be greater. See, we always say ds for the control volume will be equal to uh, delta Q by T plus entropy generation. Okay, so entropy generation. So there is no heat transfer. This term is actually equal to 0. So what is entering and leaving? It should be equal to S2 minus S1 should be equal to entropy generation. So S1 is the intake, and S2 is the this is inlet and this is outlet. So in outlet there is term number 3, and inlet there is term number 1 and 2. So I think this equation is correct actually. Okay, so our doubt is cleared now. So entropy generation is given by, see, from this entropy balance also you can see the term which is leaving is 3. So m3 into s3, that is the entropy leaving. This is the entropy entering. This is also entropy entering. So you can see entropy generation is equal to m3 s3 minus m1 s1 minus m2 s2. And what we can do is, this is, just a minute. Okay, so entropy generation, now we have divided both sides by m actually. So if you will see the first term on the right hand side, m by m becomes 1, m1 by m x, okay, and 1 minus x over m2 by m, that will be equal to 1 minus x actually. Okay, so this is clear I think to you. Then we have we can write it as entropy generation divided by mass is equal to S3. Okay, this is S3 minus S2 term because it also contains M, and multiplying with this particular value, it is equal to S3 minus S2, and then X into MS1, and this also is X, this is positive actually, plus X into MS2. So we get X into S2 minus S1. Okay, and then if you will see, if we are considering it as a gas, in that particular case we will have S3 minus S2. This is the gas which is leaving, and this is the gas at entry. So S3 minus S2 will be given by Cp log natural T3 by T1, and it is X. S2 minus S1 will be Cp log natural T2 by T1. Okay, then we have divided the left side by Cp. So S generated divided by mCp is equal to log T3 by T2 into T2 by T1, and this X is taken as the power, and the log terms, they can once they are in plus sign, they become they are multiplied to each other, so you get this particular equation. And this is nothing but this is known as ns is entropy generation number. So entropy generation number is now given as T3 by T1. Just a minute, just hang for a minute. Hello. So ns is entropy generation number, okay, which is equal to log T3 by T1, T1 raised to power 1 minus x into divided by T2 minus raised to power 1 minus x. How does it comes into picture? Actually, we have multiplied and divided this equation here by uh, T1 and T1. Okay, now you see it here. What do you see? I think you got the answer. This T1 is brought here instead of T2, so you get T3 by T1, and then so this term becomes T2 raised to power x minus 1. This term will become T2 raised to power x minus 1, so it has been taken in denominator, so it is 1 minus x. Similarly, this term is also 1 minus x. So entropy generation number becomes T3 by T1, T3 by T1 divided by T2 by T1, 1 minus x, and this T2 by T1 we have denoted as tau. If you remember, this is the value of tau, T2 by T1. So you can see it here. This is the entropy generation number. Okay, now where ns is a dimensionless quantity known as entropy generation number, which is given by entropy generated divided by m into Cp, and I know that you know m into Cp is nothing but heat capacity. Okay, so then they have written it in terms of x and 1 minus x. You can see it is T3 minus T1. Okay, uh, from equation 8.70 in equation 8.71, 8.70. So this is the value of, let's see, T3 by T1. So T3 by T1, let us see what is written here. T3 by T1. So this was T3 by T1 here. Okay. So it is x plus tau 1 minus x from the equation there. And this was T2 by T1. It is 1 minus x. Okay. If x is equal to 1, what is the meaning if x is equal to 1? X is equal to 1 or tau is equal to 1. What will happen in that particular case? The entropy generation becomes 0. Okay. What was x? X, you can see it here. This is the value of x. If it is equal to 1, means there is only one stream entering and one stream leaving actually. So it will be equal to 1 in that particular scenario. Okay. So 1, 1. So this term will go. Okay. This will become 0. I think you can calculate this value. Okay, having calculated this value, what we can do is we can calculate the loss of energy due to mixing. Work loss is given by irreversibility. Value will be equal to T naught, and this is the value of the entropy generation. This is the value of entropy generation. Okay, that is how you calculate it. Okay, now let us go to the next topic, which is availability or exergy balance. Now, this is very simple and very easy to understand. But initially, when you will go through it, you will find that it seems to be difficult, but in the end, it becomes very simple actually. Okay, what is availability or exergy balance? The availability or exergy is the maximum useful work obtainable from a system as it reaches the dead state, and you know it. Conversely, availability or exergy can be regarded as the minimum work required to bring the closed system from the dead state to the given state. Okay, see, these are two different things actually. When a there is power generation, then the power generation would be maximum when there is no irreversibility. In the second case, suppose we are compressing some gas. In that particular case, the work will be minimum when it is compressed reversibly. Okay, or when the state is changed from the dead state to some particular state actually. So in that case, the work is required actually. So where the minimum, when it is minimum work required, then it would be known as exergy. Okay, or the maximum work. See, but let us be clear. See, when you are compressing a system, the work required should be minimum. Only then it is the availability actually in that particular case. Okay, the value of exergy cannot be negative. This is very important. If a closed system were at any state other than the dead state, the system would be able to change its state spontaneously towards the dead state. This tendency would stop when the dead state is reached. No work is done to effect such a spontaneous change, since any change in state of the closed system to the dead state can be accomplished with zero work. Thus, the maximum work or the exergy cannot be negative. Okay, this is clear from here. If there is a system and we want that it should move from some particular state 1 to the dead state, then it can be brought from 1 to dead state immediately without producing anyone. That is the spontaneous change. So exergy will become 0, but it cannot be negative actually. Okay, so it cannot be negative. While energy is always conserved, exergy is not generally conserved, but it is destroyed by irreversibilities. So energy will always remain conserved, because as per first law of thermodynamics, we say that energy can neither be created nor be destroyed. Whereas with exergy, it is a different scenario. Exergy is destroyed because of the irreversibilities. So that means if there is a system in which exergy is entering and exergy is leaving, and suppose exergy entering is E1 and the exergy leaving is E2, then this is the validity that E2 has to be either less than E1 or equal to E1. That is the final condition. Equality will hold good when it is a reversible process, and inequality will hold good when it is a irreversible process. That means E2 minus E1, E1 minus E2 will be equal to exergy destroyed. I am representing it by ED. So it is written exergy in minus exergy out is equal to exergy destroyed. Exergy destroyed can be 0 for a reversible process. Now you see energy in minus energy out is equal to 0. Okay, that is the first law, and the lower one is the second law of thermodynamics. Now exergy balance for an closed system. So let us see what is a exergy balance for a closed system. Availability or exergy transfer occurs across the closed system through heat and work. So there are two things through which the work can be, exergy can transfer. That is, one is heat and other is work interactions, as shown in figure. So you are shown with a closed system. This is the boundary. This is the boundary, and then we are getting work W1 to 2 from this process, and this heat is entering. This you can say is the temperature at the boundary. Okay, and the system within is going from moving from state point 1 to 2. So there is a possibility because we are getting certain work. So the boundary is expanding also. Initial volume is V1, the final volume is V2. That is not shown in this particular diagram actually. So when we apply the first law of thermodynamics, what do we say? We say that delta Q is equal to dE plus delta W. So from this we have written E2 minus E1 is equal to integral delta Q between state point 1 and 2 because it's a path function, and then even if we don't write it, we write it in a simple way, that can also suffice, but there is a specific reason why it has been written in this manner. You will find it later on. Minus W1 to 2 for the process 1 to 2 when the system is moving from process 1 to 2. Now, from the second law of thermodynamics, we know that ds of the system has to be greater than or equal to delta Q by T. Okay, and if the system is moving from 1 to 2, so I will write that S2 minus S1 will be equal to delta Q by T from 1 to 2 plus plus entropy generation. So you can see from this equation, if I calculate the value of entropy generation, that will be equal to S2 minus S1 minus delta Q by T integral 1 to 2. This is the equation. So next what we have done is we have multiplied this whole equation by T naught. Okay, multiply here by T naught, multiply here by T naught, and multiply here by T naught, and you will get this particular equation. Now what we have done, we have taken this particular equation, and from this equation we have subtracted this equation. So let us see what do you get. So we will get E2 minus E1 minus T naught S1. You can see it here. This is the first term they have written, and then they have taken this value delta Q. This is the value of delta Q minus W. This is on the right hand side. Okay, both these terms. And this term when taken on, if we will be subtracting from this particular equation, then this term will become positive if it is on the left hand side. When it goes to the right hand side, it is negative, and this also becomes negative on the right hand side. So this is the final equation that we have got here. Okay, just see it carefully. If you have any doubt, you can stop me. I will explain it once again. Okay, don't bother much about it, because finally when I will explain you how to write the exergy balance, you won't be need to worry about all these equations actually. This is only the derivation part. Okay, now you see once again this is the same equation which is written on the previous slide. So finally this term and this term has been combined. So we get 1 minus T naught over T sigma, means this is the temperature at the boundary, into delta Q. So this is this should have been sigma here. Okay, minus W1 to 2 and T naught has generated, and the left side we have this particular term. Now do you remember what was the availability function in case of closed system? It was given by phi, which was equal to E minus T naught S plus P naught B, if you remember it. Okay, so here what we have done, when the system is moving from state point 1 to 2, we are calculating the change of exergy or the exergy change. It is equal to, you can see now from this particular equation, this is given by E2 minus E1 plus P naught into V2 minus V1 minus T naught S2 minus S1. I hope this is clear to you. Now let us see both the equations, this particular equation and this particular equation. What do you find actually? See, if you see the previous equation, we were trying to derive the value of the maximum work. Here we are calculating the available and availability. Availability is maximum useful work. So what we have done actually, we have subtracted this value. This value has been, this is the work done against the atmosphere. Okay, so this has been added to the availability part. So Otherwise, we have already calculated this value E2 minus E1. Let's see it carefully. E2 minus E1 and minus T naught S1. We can get this value from this particular equation. So what we are left with? This is A2 minus A1. This is equal to change of exergy or availability or maximum useful work. This will be equal to, we have put this value, okay, here. So you can see it is equal to 1 minus T naught over T sigma delta Q minus W1 1 to 2 minus, now this term is extra here, minus T naught as generated. Okay. So, okay, I hope that you have not understood it. I know it, you have not understood it. Now let us go back to the start of the topic once again. Okay, this was the diagram which is available to me. And now I have to write the exergy or the availability transfer exergy balance for this closed system. Okay, now let us see how to write the exergy balance. We have derived it, but I know you have not understood. Okay, I said the equation basically is nothing but it is exergy which is entering in minus exergy which is going out should be equal to exergy which is destroyed. Okay, exergy which is destroyed. Now let us try to see what is an exergy which is entering in. Okay, exergy in rather than exergy in and out, I will say that for this particular case, it should not be written as this one. This should be exergy of the system when it is at state point 1 minus exergy of the system when it is at state point 2. That should be equal to exergy destruction. Plus, we also have to see about exergy which is entering in minus exergy which is going out. Okay, because system is already having certain amount of the exergy also. It is at a particular state. So let us see, this is the initial state. This is the initial state. So I can write E1 exergy. Now let us see what is the exergy which is entering. This heat is entering. So with it we can write Q1 minus T naught divided T sigma divided by T naught. That is the work which we can get if we add a heat engine here. Okay, so this is I am writing the exergy of this heat transfer. Okay, that should be equal to or minus E2. This is the exergy of the system finally. Is there any exergy which is leaving? Yes, there is some W which is leaving the system. So minus W for the process 1 to 2, and that should be equal to exergy destroyed, and exergy destroyed is given by E naught into S generated. Okay, so what is the exergy change of the system? It is equal to E1 minus E2. See this equation, which is equal to exergy destruction plus W1 to 2 plus Q1 minus T sigma over T naught. I hope this should be the equation, and this is exergy, or I can say it is also equal to availability A1 minus A2. So A1 minus A2 is nothing but equal to exergy destroyed, and this value is nothing but T naught into S generated. Okay, T naught into S generated plus W1 to 2 plus Q1 minus T sigma over T naught. So let me see whether I have written this equation correctly or not. Okay, this is the first term on the right hand side, but let us write it here. It is written as A2 minus A1 now. So if I write it as A1 minus A2, A1 minus A2 is equal to W1 to 2. Yes, one more thing. This P into V2 minus V1 term is not written here because that work we have not taken into consideration. Work done against the atmosphere. So that has to be actually subtracted. P naught V2 minus V1. That I forgot to write actually. So let us see. Uh, so W1 to 2, this term Now this was negative. Now this is positive, so I can write minus. If I will integrate this equation, it will be q into 1 minus T naught by T sigma. Okay, I think I have written this term incorrectly. Plus, uh, okay, because now I am writing here it is plus, so it should be minus here minus P naught V2 minus V1 plus T naught as generated. This is the value. Okay, let us see what I have written. It should have been T naught by T sigma because this is the lower temperature, this is the higher temperature. Okay, T naught by T sigma. So exergy destruction T naught into S generated. This is the first term. Okay, so this is in plus sign. Entropy generation is plus sign. So you can see it here. This is plus. Okay, then this is minus P naught V2 minus V. So let us check it from here. Minus. Okay, then let us see. This is in plus this term. Here it is written in negative. Yeah, it should have come to be negative here. Yeah, so it is also correct. Then yeah, any other term W is plus. So it's plus. So I think all the things are clear. Let me explain you once again. Okay, so okay, once again let us see. We have a closed system here. Initial state is 1, final state is 2. Heat transfer Q is taking place. The temperature is T naught. Here the temperature is okay. It is I think just let me see the diagram. Yeah. Okay, the temperature at the boundary is T sigma. Here the temperature is T naught actually. Okay, so we don't know which temperature is higher and which temperature is lower actually. That is why I was confused and written it incorrectly. Okay, so T naught has been considered to be you can say lower value in this particular case because it is always work is equal to 1 minus TL over TH. So though the direction is shown to be this side, but the work will be in the opposite direction. So here the temperature is T sigma. Then we are getting certain amount of the work here W1 to 2 and any other thing. Yeah. So I can always write that exergy E1 is already there plus exergy entering. What is the exergy entering? It is the exergy of the heat 1 minus T naught divided by T sigma plus energy. Yeah, then W is going out. So W1 to 2 or W1 to plus exergy which is leaving final exergy of the system plus exergy destruction which is equal to T naught into S generated. So we will get E1 minus E2 is equal to W1 to 2 plus T naught into S generated and plus one more term will come here plus uh, T naught V1 minus V2 which can be written here as P naught into V2 minus V1 and plus anything else? Yes, minus Q1 minus T naught into T naught by T sigma. So I hope this is clear to you. Any doubt about this particular equation? Hello. Okay. Very fast. I will finish the last topic also. Yeah. Now it is exergy balance for a steady flow system. So first of all, we have written the first law of thermodynamics, which is nothing but it is equal to delta Q minus delta Ws is equal to dH plus dke plus dpe. Okay. So we have integrated this equation. So we have written, if I will integrate this equation between 1 to 2, so enthalpy will be H2 minus H1 here. So I have taken it on the left hand side. So H1 similarly plus mv1 square by 2 mgz1 plus this is q1 to 2. That should be equal to H2 plus kinetic energy plus potential energy plus work energy. So we can write in this fashion also. H2 minus H1. I have said that's term number 1. Then this is V2 square by minus V1 square by 2, a kinetic energy term plus potential energy term is equal to Q1 to 2 minus W1 to 2. Same equation which I have written here. Okay, this is the equation. Okay, I have given the numbers to each term. Enthalpy term is 1, kinetic energy term is 2, potential energy term is number 3. Then heat transfer term number 4, work transfer number 5. There is a particular reason why I am writing it here. Then we can write the entropy equation or the second law equation. So there is this diagram you can always keep in mind. This is you can say M S1 or Si which is entering, M dot S2 which is leaving. Then there is some entropy generation within the system boundary. System is you can say some heat is being transferred to the system. So delta Q by T is the entropy transfer into the system. So what we can write is actually S1. This is the entropy which is entering plus entropy transfer from the outside due to heat transfer. That should be equal to entropy which is leaving plus entropy generation within the system boundary or the control volume. So this S2 should have been here, but they have written in the left hand side. It's okay. So I think our thing is clear. So this is entry. This you can say means this is inlet and this is exit actually, or initial and final actually. So this is easy to understand. Then what we can do is we can multiply the whole equation by T naught. So you can see S1 minus S2, which terms, if you see this term I have taken and this term I have taken and multiplied both by T naught, and then this term has been multiplied by T naught, and then S generated has been multiplied by T naught. So this value is nothing but irreversibility or exergy destroyed. This is exergy destroyed. Okay, ED. So the first term, change of entropy into T naught, is term number 6. This is heat flux into T naught. This is term number 7, and entropy generation term number 8. So let us see. This is the control system which is shown to us. Once again, same thing which I was telling you. So what we have done, we have subtracted equation 2 from equation 1. This was the equation 1 actually. This one. थोड़ा ध्यान से देख लो. इस इक्वेशन में पहली टर्म क्या है, H2 माइनस H1. इस इक्वेशन में दूसरी इक्वेशन में इसमें कौन सी पहली टर्म है, T नॉट इंटू S1 माइनस S2. नंबर 6 है इसमें. तो देखो H2 माइनस H1 माइनस T नॉट S1 माइनस S2. नंबर 2 पे यहाँ पे लेफ्ट साइड पे काइनेटिक एनर्जी टर्म, पोटेंशियल एनर्जी टर्म. राइट साइड पे अब अगर हम देखते हैं तो अगर हम सब्ट्रैक्ट करेंगे तो नंबर 4 और नंबर 5 हैं. इसमें से क्या माइनस करना है, 7 और 8 को माइनस करना है. दोनों टर्म्स माइनस होंगी. और क्योंकि ये ऑलरेडी जो है अगर इस टर्म को मैं राइट साइड पे लेके जाता हूँ तो ये नेगेटिव हो जाएगी, तो वहां पे पॉजिटिव हो जाएगी नेक्स्ट इक्वेशन में. यहाँ देख लो, ये पॉजिटिव हो गई और ये जो वैल्यू है ये नेगेटिव आ जाएगी और ये रिवर्सिबिलिटी की वैल्यू आ गई हमारे पास. ये देख लो, क्योंकि इसको माइनस करा है हमने यहाँ पे. ओके. और Q12 जो टर्म नंबर 4 है और टर्म नंबर 7 है, इसको कंबाइन करके लिखा है. ठीक है. तो once again I would say there is no need to worry. I will once again write this equation. This is given here. So finally you will get this particular equation. But let me tell you how to write this particular equation, all this in a one single line, and that would be, I will tell you. We have a open system here. So there is exergy which is entering in, exergy entering in minus exergy going out. Because it is steady flow, we are not worried about within the system, exergy within the system, because that will not change actually. Then there is certain work which is going out of the system, W dot for the control volume. There is some heat transfer to the system QCV. Okay, and this is happening at this temperature T sigma. Here the temperature is T naught, and exergy associated with this value is QCV into 1 minus, okay, T sigma by T naught. And then yes, anything else? Then there will be some part of the exergy destroyed. So I can always write exergy entering in. Okay, this is entering in is nothing but you can say EI. This is entering into the control volume. Then what is entering in? Entering in is this term Q CV 1 minus T sigma by T naught. Okay, and what is leaving actually? What is leaving should be equal to exergy which is going out plus W which is going out plus there is some exergy destruction within the control volumes. There is some exergy destruction, that is actually ED, and that is nothing but E naught into S generated, or we can also say it is equal to I. Now what is the value of exergy in? Exergy in is equal to HI minus E naught SI plus VI square by 2 plus GZI multiplied by M dot. I can take this term here minus E2 which will be M2, and same values here at the outlet, and that should be equal to WCV plus irreversibility minus QCV into 1 minus T sigma by T naught. That is how simple. It's very, very simple. We can write it this way. Let us see what is written here. Okay. So it is equal to H1 minus H2 minus T naught S1 minus S2 V1 square minus V2 GZ2 minus Z1. Okay. This is the availability function actually. Okay. Now we are calculating the uh, heat transfer terms also. So you can see this is the heat transfer term, this is work transfer term, this is the availability change. Okay, availability function actually. This is availability function minus ICV equal to 0. So you can see it here. We have written the same equation. So this is nothing but this term is which is written there is this is AFI, availability function at inlet. This is availability function at outlet. Okay, and that is equal to WCV. So if you will see it would be in the minus. It's in the minus. IQI it should be. If you will see I, it should be negative in the previous equation. Yes, it is negative. Let us see heat transfer term. If we will take it on the left hand side, it will be positive. It's positive. It's okay. So I think this should be clear to you. Any doubt? Tell me. Okay. Any questions? You can ask.